proposed these ideas that turn out to be absolutely true. Well, I shouldn't say absolutely. I mean, Dalton wasn't right in every detail of what he said, but in the overarching description he came up with, it was remarkable. So what did he say? He said all matter is made of atoms and that atoms are indivisible and indestructible. Point one. Point two, all atoms of a given element are identical in mass and properties. So we all know what carbon is, I think. So all this is saying really is an atom of carbon compared to another atom of carbon compared to another atom of carbon is going to have the same mass. And carbon is carbon, right? It's going to have similar properties. And those properties are going to be different from sodium, going to be different from oxygen, and so on down the list. He then, in his atomic theory, proposed that compounds are formed by a combination of two or more different kinds of atoms. We actually already went over that last week, right? And we talked about that, right? So Dalton was the first one to really propose that. What else? A chemical reaction is a rearrangement of atoms. So we're going to look at all this in some detail, but at the time, people were not, in 1808, this was not at all clear that any of this was true. And in fact, Dalton encountered a fair amount of resistance in terms of, okay, does anyone know Noah Barrow? Does anyone, this is just a little break here. He's having a hard time. Yeah, I see Valerie. He says times on black. Can anyone send him a link? Does anyone, Valerie, do you, for example? Okay, thank you, Valerie. I assume the rest of you are not really having any trouble here. Is everything cool? Okay, I don't know what to do about Noah. Let me just take 1 second to respond to him. Yeah, okay. Noah, you are seeing the right thing. Just click on the 3 dots and then join session. Okay, that's all I can do for Noah. Okay, so moving right along here. So if we're going to talk about atoms combining, which is, or compounds being formed by a combination of 2 or more different kinds of atoms, well then we need to talk about the law of definite proportions, sometimes referred to as the law of constant composition. So all this is really saying is that if we have some compound, let's say it's CO2, right? Well, the carbon in a molecule, and in a molecule, or the compound carbon dioxide, atom of carbon is going to have a certain mass, and 2 atoms of oxygen are going to have a certain mass. And it's important to note that there's a consistency, there's a uniformity here, right? These elements are always going to combine in the same proportion by mass. Now, we haven't discussed yet how we can measure the masses of elements and so on and so forth. We will get there big time. But for now, it suffices to say that for any given compound, methane, carbon dioxide, hydrogen chloride, pick a compound, right? The elements will combine in the same proportion by mass. Now, a related law, which, you know, you have to really pay close attention here to see why these two are even different, because the law of multiple proportions states that when 2 elements react to form more than one compound, a fixed mass of one element will react with the masses of the other element in a ratio of small whole numbers. So here we're going back to this idea of fixed proportions of masses, which is already stated in the law of definite proportions. But let me give you a what if here. Well, here's the what if below, actually. Carbon monoxide is one carbon atom and one oxygen atom combining together in this fixed proportion. But what about the compound I just mentioned above, carbon dioxide? Well, guess what? Here we have one molecule of carbon combining with two molecules of oxygen in a different ratio. Here it's 1-to-1, and here it's 2-to-1. Now, this might not seem like a super big deal, but it's actually quite important. You know, carbon monoxide is a very different compound from carbon dioxide. Just like something like water, H2O, is a very different compound from hydrogen peroxide, H2O2. But what all compounds share in common is that the ratio, the elements that form the compound always combine in a ratio of small whole numbers. We don't have H2O 1.5, right? What do you think that is? Why do you think we don't have H2O 1.5? Rachel? Thank you. Teresa beat you to the punch. You cannot split an element, right? Unless it's a hydrogen bomb, which none of us really want. So this gets back to Dalton's idea that atoms are indivisible, which is, you could argue that that's both correct and not correct, right? I mean, technically, yes, we can split an atom, but normally it doesn't happen, right? We have to, as human beings, we have to go to great lengths to split atoms. Okay. So what becomes interesting in terms of these fixed proportions and strict rules about, you know, how elements must combine in certain ratios guided by small whole numbers, is this in turn allows us, when we're talking about chemical reactions, to arrive at the conclusion that if atoms are neither created nor destroyed during a chemical change or a chemical reaction, which is true, then the total mass of matter present when matter changes from one type to another will remain constant. This is the law, this relates really to the law of conservation of matter. And it's important. So, I thought, yeah, I have a slide here that's going to demonstrate this. So let's say we have, God, I'm having another student. Oh no, it's okay. Oh, good Lord. Atoms of element X, let's say, combine with atoms of element Y. And they do so in some definite way, in some proportional way, right? So let's say these compounds form the molecules, these atoms that you see here, atoms of X and atoms of Y, form the molecules that you see here. That means we're going to get 8x2. These are our x's here, right? Combining with a single y in the ratio of 2-to-1. Notice that nothing is lost or gained here. So this is just a demonstration of matter not being created or destroyed in the course of a chemical reaction. Now, one thing we're going to get to later is, and I might as well, sometimes I like introducing things a little early here. What if we had, so let me give you a thought question here. What if we had 14y here? instead of 8y. What would your prediction be for this chemical reaction? Teresa, that wasn't a problem, by the way. You just jumped in. That's fine. So if we took 16x and we were conducting some chemical reaction and we added 14y, what do you guys, who would like to hazard a guess as to what the outcome would be? Would this change? Would this, would the outcome in terms of what we could get change? So instead, Eric, I'm saying instead of, okay, so what? Interesting, interesting. We're getting a lot of really interesting comments here. So it might be H2O2. Interesting thought. Definitely an interesting thought. But let's say this is not a situation. Let's say this is a situation where these X and Y atoms can only combine in one way to create this X2Y compound. So X2Y2 is not a possibility. So I think Eric is kind of at the right answer here. What, so okay, first, to make this simpler, will the amount of if we add 14y to 16x, will the amount of product that we get change? Will it go up to 10x2y, for example? Yes or no? No, it can't, right? Because we don't have 20x. Hi, everyone. Sorry, I know that's never pleasant, but it just is bound to happen sometimes with temporary internet things. So I'm going to keep my video off just so that maybe that will help. It just, yeah, it's part of the, yeah. So I rejoined. Everything is cool. Fear not. We will get through this always, unless there's some major problem, but hopefully that will not be the case. Okay, so back to this idea. Where were we? So the point I was trying to make here is that if you have, for example, 14y, or let's say 10y, well, the deal is you will have just extra y left over. And this is something we're going to be talking about extensively when we get to limiting reagent. But I just wanted to introduce it to you now. It just so happens under the current circumstances as shown in this slide, we have the perfect amount of X reacting with the perfect amount of Y to create this. But even if we had extra Y, matter would not be created or destroyed. It would just mean that we didn't use up all the Y. So that's just something for you to start thinking about right away, because stoichiometry, this proportional combining of elements to form new compounds, is an absolutely proportional exercise. And I want you to keep that in mind from the very beginning of the course. Okay, so now we can turn our attention to what are atoms made of. Let's not worry about nuclear. Abraham, you're talking about nuclear chemistry right now, which is a whole different kettle of fish. We're not going to be talking about that in this course. I mean, it's a great point. So yes, in nuclear decay, you can have matter transformed into energy, but that's really not in the scope of what we're talking about right now. Okay, so what are atoms made of? Great equation, though. Love that equation. So what are atoms made of? Electrons, protons, and neutrons. If you've had any chemistry whatsoever, you already know this. But so it's either unusually, I would say, yeah, you might not know that at all, but I think most of you probably already know that. Okay, so how are these subatomic particles? Well, first of all, let's talk a little bit, really quick, let's talk about how they were discovered, because I was, very emphatic about the fact that when Dalton was proposing atoms as the basis for matter, he certainly didn't really know whether they existed, and he certainly also had no clue about subatomic particles. So we call protons, electrons, and neutrons subatomic particles. And in a very cool experiment, a gentleman by the name of J.G. Thomson was one of the first scientists to provide some actual proof for the existence of the electron. And the way he did it was he took a vacuum tube, which is this blue thing here, and he hooked it up to a high voltage source. So voltage, all batteries and all sources of voltage, it's basically a stream of electrons, right? No one knew that at the time, but if you direct these electrons from our voltage source through a cathode and an anode, which are these negatively and positively charged plates, respectively, well, you can guide this beam of electrons through an electromagnetic field, as you see here. And depending on what was turned on when, in terms of this electromagnetic field, and orientation, basically, electrons could be deflected in different ways because of their charge and because of their interactions with an electromagnetic field. So this was the first time any scientist ever conducted an experiment that demonstrated that these strange creatures called electrons might even exist. So he could not get at the actual mass of an electron because electrons do have mass, but he was able to come up with a mass to charge ratio, which is the charge of an electron relative to its mass is negative 1.6 times 10 to the 8 coulombs, which is a measure of electrical charge per gram. This is not something you're expected to memorize or remember, but it is good to know that this was a groundbreaking experiment. And as I mentioned, was really the first to demonstrate the potential existence of electrons. Now, however, we know that electrons are not the only subatomic particle. So this is really I mean, all these experiments are cool, but this Rutherford experiment is really my favorite because it's just such a cool thing. I hope to convince you it's cool. So what did he do? So he not only did he accomplish demonstrating the existence of the proton, but he also was able to demonstrate that this proton, this positively charged subatomic particle, is in all likelihood found in something called the atomic nucleus. Again, something today we know to be true, but keeping perspective was a complete unknown at the time. So what's the setup here? Well, instead of having a voltage source, this time we have something called an alpha particle emitter. Now, I don't expect you to know what an alpha particle is, but it is something that pertains to nuclear chemistry. And it is a positively charged particle that emits in the process of radioactive decay. So now instead of a beam of electrons, we have a beam of positively charged particles being directed a very thin piece of gold foil. So if you imagine that we zoom in on that, what's happening? Well, these alpha particles are coming in a stream at this gold foil, which is surrounded by this detecting screen that you see here. Now, very occasionally, if you take a look at this, very occasionally, the alpha particles would bounce back or they would be deflected, as you see here. I mean, both of these are really deflections, but sometimes they would go like more straight back. Sometimes they would just go off to the right or the left. The great majority of the time, they would just go right through. So here you are, you're Rutherford. You don't know really what's going on here, but you're trying to figure out what's going on here. You probably know that your alpha particle. God damn it. Okay, brief interruption. Thank God that was mercifully short. Okay, so now you're Rutherford, as I was just saying. Okay, first of all, Diana, these are not important to remember. These are not electrons. These are not bouncing electrons. These are alpha particles and they're positively charged. Doesn't, honestly, what this gold screen is, what the detecting screen is made of, I'm not even sure, but presumably there would be some kind of mark left behind. But I'm glad you actually said electrons, because keep in mind that this is now we've moved on from electrons and we're trying to identify protons, and we're trying to figure out where they are. Yeah, because Christian, yes, because the only time, and why do you say that, Christian? Why do you, yeah, something like X-ray film, Diana, exactly. So Christian, why does this experiment show to you that this positive charge is concentrated in the nucleus, or anyone else for that matter? What would be your rationale for saying that protons are concentrated in the nucleus? Well, Michaela, yes, that's one, but I'm talking about localization here. Think of this in a statistical sort of way. Statistically speaking, like, yeah, because thank you, Abraham. It only bounces off when it hits dead center, and that's a rare event. Most of the time, these alpha particles are just charging through and not deterred in any way. It's only on that rare occasion when they hit the nucleus that they bounce back. And that's because positive charges are repelled by other positive charges. So there's actually quite a few things going on here, right? It has to do with the localization of the nucleus, which we're going to see in a minute is very tiny. The nucleus of an atom, of any atom, very tiny with respect to the overall molecule. So let's take a look at that. So in Rutherford, that's the experiment we just described, in his model of the atom, he proposed that there was a very tiny nucleus composed of protons and neutrons. Now we're not going through all, this is just a sneak peek at some of the experiments that went on. There's something called the Millikan oil drop experiment. That's described in the book. We're not going to worry about that today. I just want to give you a flavor for how these ideas were developed and the experiments behind them. So Rutherford came up with this model that said that we have protons and neutrons condensed in this very small nucleus, and then this very large sphere around that nucleus. And now I want to try to give you a sense of the scale that we're talking about. So an atomic radius is 100 picometers. And if we convert that to meters, we get 1 times 10 to the negative 10 meters. So that's kind of impossible for us to imagine, right? So this is, but keep in mind, this is the whole atom. We're talking about the radius of this whole atom, right? The nuclear radius, by comparison, is only 5 times 10 to the negative 3rd picometers, or 5 times 10 to the negative 15 meters. This is an order of magnitude that is 15 times smaller. That's enormous. So, but let's put that in terms of something that we can relate to more than picometers, which would be the Houston Astrodome, or the favorite stadium of your choice, right? The Houston Astrodome is picked here because it's a covered sports stadium, so we can think of it more like representing an atom, and we imagine that, and that's even too big, right? We imagine that the nucleus would be like a marble on the 50-yard line. That's how small it is relative to all the space that the electrons have to roam around in. And we're going to be talking about protons, neutrons, and electrons, particularly electrons, a lot in this course. So let's zoom into a lithium atom, or lithium metal, just as an example. And we're going to go from the macroscopic, which is something we can see with the human eye, right? And we're going to drill down further and further, all the way to like trying to imagine atoms, and then the nucleus and the electrons and the nuclear diameter. So the first, level of drill down would just be to imagine the atoms themselves. Now, lithium is a metal.